My name's Bonnie Hafferkamp. I teach in our biomedical engineering department here, and on behalf of the Illinois Institute of Technology, Armour College of Engineering, I would like to welcome you to the American Institute of Chemical Engineers Midwestern Conference and to this program that was put together specifically for high school students. So today in this presentation, you're going to learn a lot about what are the different areas of engineering, because lots of times you think, this is kind of fun, this engineering, but I don't really know exactly what it is, or I don't know what all the different areas of engineering are. And there actually are quite a few areas of engineering. And anyone who really likes to solve problems, likes math, etc., as you're going to hear, can find an area of engineering that really matches what your interests are. And that's what we're hoping to do in the next 45 minutes, is really expose you to what some of those opportunities are. And I was fortunate enough to be able to recruit one of my students in biomedical engineering, Tim Irle, who is going to discuss this with you and help you see what what you can do as an engineer in the future. So let's give Tim a warm welcome.
Thank you very much. My name is Tim Irle. I'm an undergraduate student at Illinois Tech's Armour College of Engineering. Specifically, I am a biomedical engineer, and I will be graduating this May 2016. Yes. Oh, thank you. Thank you. It feels so good. Which means I'm a student, just like you guys. So my goal here today is to share with you my love for engineering. We're going to talk about different disciplines you can study within engineering and answer any and all questions you may have about engineering. So I'm going to begin by going out on a limb and making an assumption that one of the reasons you're here today is that you happen to be good at math. If not, don't freak out. It is okay. It's a skill you can build like any other. But ask any engineer and they will tell you that math is the subject that binds us together. It unites us. It is a language like any other you hear on the street. You can read it. You can write it. It is a language of power. Using math, you can read and interpret the world around you. You can also write in math as an act of creation. Once you become fluent in this language, you begin to see the world a little differently. You begin to see the world as an engineer. Let's take this piece of paper. Now, an English major may look at this and say, I see a blank page. But let me tell you what I see. I see an 8 by 11 piece of composite wood fiber composed of millions upon millions of atoms constantly in motion, each one vibrating at a unique frequency. I see raw grains of material, like a jigsaw puzzle, bursting with energy at the seams. I see the results of its manufacturing and the specific orientation of those grains. Because I see all these things, I know that this flimsy piece of paper is actually quite strong in exactly one direction. Observe. Now, I'm going to make a tiny tear. It's a small detail, one that any psychology or business major may miss. But engineers see all details, big and small. And because I see this tear, I know that it's actually a focal point for applied stress. Because I see this detail, it gives me the power to do this. And that's what engineering is. It is power. It is the power to change anything, everything. The air we breathe, the water we drink, the roads we walk, any skyscraper you've ever admired, moon landings, electrical cars, hunger, disease, social injustice. Have you ever looked at the world and said, somebody should change that? Engineering gives you the power to do so. I'm going to show you some wondrous innovations from engineering today. But before we do, a cautionary tale about details. Some details are terrible. Some details, no matter how small, can lead to catastrophic results if overlooked. This is the Tacoma Bridge.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. the actual collapse of the world's third largest suspension bridge. Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
And a dog. That part gets me every time. I mean, I care about that dog. I don't want that dog to die. So, the Tacoma Bridge. Now, I want you to imagine this bridge as a guitar string strung across a river, okay? Pinned at either end. And the detail they didn't account for was wind. Now, the wind is like a guitar pick strumming this string. And as the wind hits it, it adds energy to it. And all of a sudden, this bridge becomes a wave. And as the wind added more and more energy to it, the wave got bigger and bigger until it hit its resonance frequency and the whole thing fell apart. That's crazy, right? Respect the details. Now, fun stuff. So the first discipline we're going to talk about is mechanical engineers. Do we have any gearheads in the house? Anybody who wants to be a mechanical engineer? Anybody who loves cars? Yes, there's always some. You two are great. So, mechanical engineers and also materials engineers use their power to create things such as cars, planes, moving parts, tools, machinery systems. And where materials engineers come into play is they make the actual, materials to build these things. Metal, plastic, polymers. The results of which are always fun and exciting. And I'm going to show you a video of that right now. Okay, we just saw a lot of things happening, a lot of moving parts. We saw brake pads, shock absorbers, I saw some pistons moving. Altogether, these represent a solution. As engineers, we know that every solution stems from a problem, and every problem has a solution. So I'm curious if you guys can think of anything that, for this solution, what problems they might have been trying to account for, or problems they came across the way, and I have some very exciting news for you. You ask a question, you get a hat. That's right. So we offer incentives here. So if anybody can think of any problems they might have run into, anybody at all, raise your hand. Yes, right there in the back. Well, I'll tell you what, this gentleman's going to hand you a mic right now because I couldn't quite hear you.
Overheating.
Overheating? Yes. Perfect answer. That's exactly right. So this is a traditional combustion engine, and the problem with that is you're trying to contain an explosion, which is very difficult, right? So you have to account for that heat. You have to find a way to dissipate that heat. Materials engineers, this is a lot of times where they come into play. We know the principles behind making an efficient engine, but the problem is heat. It's always heat. How do you hold it? How do you contain it? How do you dissipate it? Excellent answer. Thank you very much. Very hat-worthy. All right, one more question. Who wants a yes? My man, what you got?
The brake pads can malfunction and just not work.
Yeah. One more time, please.
The brake pads can malfunction and just stop working.
Exactly. The brake pads can malfunction and not work. This whole thing kind of falls apart if the brakes don't work, right? Plus, even deeper into that, like how quickly do you need to stop? How fast do you need to account for? How long should the brake pads last? We got to make them cost effective, or otherwise nobody's going to buy this thing. All right, excellent questions. Aerospace engineers, any future astronauts around here? Who wants to go to space? Yes, right? It's great. So aerospace, we know a lot of the things they use. They use their power to make, let's see, satellites, space shuttles, rockets, all types of things. In fact, one of those things I'm going to show you right now.
LD, verify go for launch.
SpaceX Falcon 9 Orbcom, go for launch.
3, 2, 1. Liftoff for Falcon 9.
First stage propulsion is nominal. Vehicle slide down to nominal. Stage separation confirmed.
Okay, so if you're not thinking about it now, I guarantee you in about 4 years you're going to start thinking about jobs. And what's exciting about spaceflight is it actually recently become privatized. What you saw there was made by the company SpaceX, who made the Falcon 9 rocket, which was the first one to take off and land vertically, which I think is incredibly impressive. And you know, there's going to be lots of problems dealing with that. So can anybody think of like the problem they might have to account for, or problems they might have run into along the way? Yes, future astronaut.
Aerodynamics?
Would you say that one more time?
Aerodynamics?
Aerodynamics, yes. It all boils down to aerodynamics, how things move through air and space. We'll have to account for things like air resistance. They'll model those materials. We wanted to design it so that it behaves a very specific way. Excellent answer. Thank you very much. What you got, buddy?
The friction of the air.
Yeah, the friction of the air, right? Definitely. So air resistance is a thing we have to deal with all the time. Have you ever been, everybody does this. Have you ever been riding in a car and you stick your hand out the window and you do this, right? Or you put it up and you just, whoa, see how far it gets pushed back? That's air resistance. Small things, right, don't experience much, so they're not pushed too far against. But when you make your hand flat, you experience more air resistance and friction, energy, lots of things we have to account for. Any other questions?
Yeah, they have to account for like the thrust, so like it propels the rocket forward but doesn't destroy it in the process.
Yeah, thrust. Trajectory. You know, the universe is an incredibly big place. And how do we design something to get in an exact location in that big place? We have to deal with trajectory, thrust, how fast it's going to get there. Time is a thing engineers experience and have to account for a lot. Excellent questions. You guys are doing great. Okay, so computer engineers make, well, computers, right? They make computers. They use their power to deal with things such as designing PS4s, Xbox Ones, video games, virtual reality headsets. I'm particularly excited about the Oculus Rift coming out soon. They're going to deal with, as opposed to computer scientists who only do coding, they deal with software and hardware and make integrated systems. And oftentimes, you know, engineering is an interdisciplinary field, which means we'll work as teams with other people from other disciplines. And they'll work hand in hand with our next field, electrical engineers. Electrical engineers use their power to make power grids, electronics, circuit boards, wires, power grid systems, clean energy systems, solar. Together, a team of computer and electrical engineers designed our next product. That is called the secret bracelet, which is crazy. I don't know if you saw that, but it's a bracelet that projects the screen actually onto your arm. Who here can think of problems that they might have encountered trying to design this crazy solution? Let's see. In the back right.
Making it waterproof?
Making it waterproof, right? Electricity and water, we know, are not the best of friends. So we have to account for that. We have to maybe insulate the device, find maybe different materials that act a specific way in order for it to function. Excellent. Fantastic question. Let's see. Right here. What you got?
Radiation.
Radiation. Yeah, energy. We always have to account for the dissipation and radiation of energy. How is it going to affect the behavior of the device? How are we going to account for it, design it? Excellent answer. Very hat-worthy. Who's next? Right here.
Where they put like the battery and like the storage on it.
Yeah, where do you put the battery? And how big is the battery going to be? You know, we have so many incredible inventions today. A big thing that pops up over and over again is battery life. If your incredible device only works for 30 seconds, not many people are going to want to use it. We want batteries that can last us days, if not longer, weeks. Excellent. Fantastic. All right, maybe one more question. All right. What you got right here in the middle? Yeah, we're going to hand you a mic right now.
How would the touchscreen work?
Yeah, how's this thing going to work? It's projecting light. I mean, I can only make some educated guesses here. I'm going to make some assumptions, but maybe if you bend the path of light a certain way, and what sort of surface is it going to project on? Like, a very clever lady pointed out to me that it might have to interact with hair. I'm going to admit this to you guys. I have kind of hairy arms. Will this thing even work for me? Am I going to want to buy it? I don't know. So great answer. Okay. Environmental engineers. Environmental engineers use their power to design such things as waste treatment facilities, waste disposal systems, air filtration units. They use their power to make this world a cleaner and, in my opinion, better place. And again, they'll work hand in hand with another field called civil and architectural engineering. These guys will use their power to design skyscrapers, buildings, bridges, and in fact, a team of them, of environmental engineers, civil and architectural engineers, came together and designed this skyscraper and built it in 30 days. Now I'm just going to skip ahead a little bit and show you it in action. Day 0, nothing. Day 30, skyscraper. I think that's pretty incredible. So, problems. There's lots of problems. We saw things they were working on. They had to account for several things, and you guys, your hands are up already. I'm loving this. This is great. All right, somebody new. There, towards the back left, pointing right at you. What do you think?
So you have to account for natural disasters to make sure the building is stable.
Would you say that one more time?
So you have to account for natural disasters like earthquakes and high winds.
Oh, most definitely, yes. We saw they were worried about making it earthquake resistant, which introduces a whole host of problems. I imagine angles of plates coming together, how much energy, how long does it have to experience this earthquake? How strong is strong enough? These are things we have to account for. Excellent question. Thank you very much. Who's next? All right, right here. What are you thinking?
Whether it's wind resistant, kind of in like
Yeah.
addition to the.
Wind keeps popping up, right? It's everywhere. We can't seem to escape it. It's causing us so many problems. So if it's a tall building, I imagine it's going to be experiencing lots of wind up top. We got to make sure it's strong. Make sure these materials don't bend or break. Design it in such a way. Very good. Excellent. Thank you very much. Who's next? Jason, that looks like a great question right there.
Materials?
Yeah, materials. What metals do we use? What polymers do we use? How strong are they? If we take this metal and we try to bend it, at what point does it break? A lot of researchers have spent a lot of time investigating different materials to see at exactly which point they break, so that we can build these and know that they're safe up to a certain point. Very, very, very good. Thank you. All right, chemical engineers. Chemical engineers use their power to make practically everything around you. They make contact lenses, cell phone batteries, glues, the soles of my shoes, markers, crayons, medicine, vaccines. This is so versatile that, in fact, a lot of the principles of chemical engineering are also used in combination with our next field, biomedical engineering. Biomedical engineers use their power to make medical devices, prosthetics, X-ray machines, MRIs, artificial organs. And in fact, a team of chemical and biomedical engineers work together to design our next innovation.
I'm Dr. Benasser, and my lab makes ears. The invention that we've discovered is a way to print living cells in a material that can be used to reconstruct tissues in the body. My laboratory is interested in regenerating cartilage wherever it's found in the body. The process starts with a scan of an ear. We sit someone down in a chair, and we have a camera that spins around their head and takes a 3D image of their head. We then can very precisely map out the topology of the ear. The next kind of key step is developing the ink for this printer. This ink is actually a living ink. It contains living cells. It's alive when we put it into the printer. It's alive when it comes out of the printer. The real power of the printing technique is that it can be used to make geometries that you just can't make with any other technique. You can make parts with holes in them. We can layer and cover and put different cells next to each other to create really the complex organs that make up our bodies. And after 2 months in an incubator, the tissue fills in and looks white, just like real cartilage. The implants that we're making are not rubber or plastic. They are alive.
They are alive. I don't know if you guys caught that, but he just 3D printed an ear. So that is a wonderful solution that is going to involve, of course, lots of problems. Any guesses? Anybody? Yes. I'll tell you what, we hold on it for just 1 second. We're going to get your microphone so everybody can hear your wonderful question.
Radiation when it comes to like building those machines, like
Yeah, energy and building these things. And you know, our bodies are designed a very specific way to not let outside things in. So and they're very, very good at accounting for, through our inflammatory response, rejecting those things. So we have to make sure they're accepted. Excellent. Good job. Right there in the back.
How it interacts with other cells?
Yeah, how it interacts with other cells. Or is it going to acceptance is something he brought up. And how do we feed nutrients to this ear and make sure it's nourished and stays viable? Excellent, excellent. Good job. Thank you. All right, last one.
Basically like finer points of the ear, making sure that it's exactly the same as the ear you're making.
That's exactly right. Make it exactly the same as the ear you're making. So medical imaging is a big part of biomedical engineering right now. It's a very big and up-and-coming topic. So we have to scan it and make sure that the product we're designing is going to look and be the shape that it's supposed to be. Excellent. Fantastic. All right. So all of these programs that I mentioned today are taught right here at Illinois Tech's Armour College of Engineering across 5 departments. Within those 5 departments, we have 9 ABET accredited Bachelor of Science programs: aerospace engineering, architectural engineering, biomedical engineering, civil engineering, chemical engineering, computer engineering, electrical engineering, mechanical engineering, and material science engineering. Now, if you want to know information, we also have a very cool program this summer that's going to offer lots of different classes, but 2 of which we put up here. Intro to Robotics, where you're going to actually get to design, build, and program a Lego EV3 robot, which is just beyond cool. And Introduction to Engineering and Design, where you'll learn the principles used to design some of the innovations you saw today. Now, if there is one message I want to leave you guys with, it is this. Engineering gives you the power to change anything. It gives you the ability. It has given me the ability to make my dreams a reality. We live in a technological age where engineers are uniquely poised to have a direct and powerful and positive impact on this world. It is a noble calling, and I believe that each and every one of you are capable of pursuing it. My name is Tim Irle. I am a biomedical engineer at Illinois Tech's Armour College of Engineering, and I thank you very much for your time today. Questions? Do we have time for questions? All right, I can give you 3 questions. So is there anything that we didn't get to that you'd really like to hear today? Anybody? Questions? How things are made? Are you thinking about studying a particular field of engineering? Would you like to know more about it? Anybody? Yeah, what are you thinking?
It's actually a bit personal, but did you always want to be an engineer growing up?
No, I discovered it really late in life. I have lived a very unique zigzag path. So what brought me back to engineering is actually, what brought me to engineering are 2 things. The job outlook, I went back to school 4 years ago to create a more secure future for my family. And I have always personally found success following my passion, and I have always loved biotech. There is something so insanely cool about taking what used to be science fiction and making it science fact. I nerd out about that every day, all day. And if you're going to do something challenging, and don't get me wrong, engineering is challenging, it might as well be something that you love. So if I could recommend anything, it's find a discipline, any of the ones I've shown you today that you're interested in, follow that one, because that passion is going to carry you through the challenges. Does that answer your question?
Yeah.
Excellent, thank you. Anybody else? Yeah, what are you thinking? Yeah, you.
Besides math and the other skills you showed us today, what other skills would you need to become an engineer?
So what skills would you need to be an engineer? Are you thinking like subjects? What subjects would you study?
Yeah,
definitely.
Math.
Well, beyond math, the skill you're going to learn in any discipline is problem solving. How do you assess a situation, identify the problem, break it down into components you can solve, and then execute them. Specifically, you're going to get into physics if you're an electrical engineer. Biomedical, my particular field, incorporates a lot. I learned a little bit of chemical and mechanical, and also some biology, like physiology, like how the body is constructed. So you're going to, depending on which application, in civils, they're going to do mechanical, physics, how things bend and break. If you're going to do chemical, you're going to do, of course, chemistry. So it depends on which field, but it's going to be, you pick a specific science and it's paired with math is typically how it works to achieve the outcome. Excellent.
Thank you.
I think we have time for one more. Is that correct? Okay. Jason, I think this is an excellent question right here.
How many years do you have to take in order to be like a certified engineer?
How many years for an engineering degree? Yeah. It's different for everybody. It depends on how many courses you want to take at any given time. For me, it ended up being about 4 to 5 years. I transferred in, so it was different. But I would say 4 to 5 years is a safe estimate, anywhere between in there. Depends on how many classes you want to take at a given time, what works for you as an individual. All right. Unfortunately, I think that's all the time we have questions for today. Thank you so much for having me. It's been a pleasure.